Yes, yes, it is full screen now.
Yes.
Do you see my presentation?
Yes, sir.
I think first slide is visible. Feynman lectures.
Yes,
I
sir.
can hear
Chapter 1.
you earlier, but suddenly it stopped. I don't know why. Recheck again. Hello.
First slide is visible.
Ah, yes.
Visible. Okay. Now I can hear you, and you can hear me now, right? Okay.
Hmm.
Okay. Right. We'll start now. One second. Right. So good afternoon, all. Good afternoon to all the
Good afternoon.
participants. Yeah. So thanks to the Charusat team for initiating a discussion with Professor Feynman's lectures. So this is quite an interesting task. So what we see today is an overview of the chapter 1. Because chapter 1, of course, was very difficult if you read through. Because after, if you say we are a BSc or MSc student, the chapter 1 is somewhat different to us when you read it. After that, say you are a PhD student, the chapter 1 is, again, it may be in a different note. After that, when you are a faculty, if you are teaching someone, the chapter 1, if you read again, this time it is looked in a different way. The way how you take it is entirely different than what was before when you're at BSc or MSc and you're reading when you're giving some exams. So I'm going to discuss few things that reflects after our year-long research and so on, and how the chapter 1 is appearing to me right now. So with this disclaimer, we will see a few things what Professor Feynman has in this chapter 1. Okay, so I'm Bala. I'm from the Physical Research Laboratory. What you see here is the background of our laboratory, the astrochemistry lab. But somehow, you have a lot in connection with Professor Feynman's discussion. So I'm just putting this background here. Slowly, we will see how it goes inside. Okay, right. To begin with, Professor Feynman, in his Feynman lectures, he has given the foreword. It's a foreword by Professor Feynman. He says that it is impossible to learn very much by simply sitting in a lecture, or even by simply doing problems that are assigned. Was he's right? Because all of us knows he's right. But in our modern times, we have so many students to teach, indeed, that we have to try to find some substitute for the ideal. I hope we can. Perhaps his lectures can make some contribution. Indeed, we can see a lot of there is background noise. Somebody's mic is on. You can hear a lot of background noise.
Others, please. So mute your mic. Or
Yeah, there was some background noise. Okay, right, we'll continue. So he says that perhaps in some small place where there are individual teachers and students, they may get some inspiration or some ideas from the lectures. Of course, he is right. And over the decades, his lectures have been inspiring. And if I'm not wrong, it has inspired many people to take up research. Perhaps they will have fun thinking them through or going on to develop some of the ideas further. Hello, there is some background noise. Can you hear me? Okay.
Yes, sir.
I'll continue. Yeah. So perhaps he says they will have fun thinking them through or going on to develop some of the ideas further. Certainly, yes, we have experienced it. Right. After the foreword, chapter 1, atoms in motion. Like I said earlier, if you are in a BSc or MSc or research time, and now it's a faculty time, it's all different that how you look at these three words, atoms in motion. And those days, when you say atoms in motion, we say, okay, atoms in the suppose you have this the water which is boiled, and then you are in the chemistry lab, you are looking at some reactions and so on. That is where we think atoms in motion. But then when you're a researcher, okay, yes, okay, atoms are in motion, not just on planet Earth, it may be elsewhere and so on. But after understanding what is happening with the atoms, the molecules and so on, we see that perhaps I have seen this in some of the documentaries. They say it is the universe that is looking at the universe. Of course, we are made of atoms. Like Carl Sagan says, we are stardust. So atoms in motion. We are all atoms. We are all molecules, and it is the atoms in motion. Okay. Right. So as I said, the way how you look at it. Now, atoms in motion, yes, and how we know and what is the truth and what is the science. So according to Professor Richard Feynman, the principle of science, the definition almost is the following. The background noise. Someone's mic is on. Okay, now it's on. So the principle of science, the definition almost is the following. That's what Professor Feynman says. The test of all knowledge is experiment. Experiment is the sole judge of scientific truth. A week ago, when we are at Charasat University doing the inauguration, I think Professor Joshipura mentioned that Professor Feynman told, if everything in this world is gone, at least leave one knowledge, that matter is made up of atoms. Okay? So it is the experiments that told us that atoms are the basis of all. Okay? Perhaps we all know that famous saying, which our teachers have told us. Of course, my teacher has told me: theory guides and experiment decides. This is what we know. And here we say from Professor Richard Feynman's words that the test of all knowledge is experiment. Experiment is the sole judge of scientific truth. That only. And few more things. So as I said again, these are my way of looking at it. So you may have a different way of looking at the chapter 1. In fact, everything we know is only some kind of approximation, according to Professor Feynman. And I totally agree with him. Because we know that all of noise coming from the background.
Please, like, kindly.
Can you hear me now?
Yeah, audible.
Yeah. Okay. Fine. Because I was not sure that noise stopped and.
Somebody kept their mic
Again,
on.
the
I'm
noise
not
is
able to
coming.
place.
Yeah. Can you please find that mic, which one it is? Not from my side. Any noise. Still hear that noise is still there. Okay, now it's not there. We'll continue. Right. In fact, everything we know is only some kind of approximation. I agree with him. Because we know that we do not know all the laws as yet. There was some discussion I know among a few professors, which have been part of along in one of the coffee table. There was some discussion that they say that, of course, most of the fundamental things have been discovered already, and most of the laws has been known. The natural laws, the nature's law, we know. But the more we learn, there may be something hidden out there. So I still go with Professor Feynman that we do not know all the laws yet. Therefore, things must be learned only to be unlearned again, are more likely to be corrected. Certainly, yes, that's we know from the case of Newton and Einstein, right? Something which is important when we talk about Feynman's lectures is to find some analog. It's not the noise. Okay,
The noise is so much there.
yeah, something. I've checked it in my side. There is no noise from my side. Right here. Not from my side. Some is better now. We'll continue. Okay, so the analog part, what he had talked about in his chapter 1 in explaining atoms. Of course, it's very important for us if you want to tell the young generation, even from school level, what an atom is. So we can say that the atom is of 1 or 2 angstroms, and we have to tell them what is an angstrom, what are the units, and how we get these numbers right, and so on. But an analog of it will be very much useful, and which will be grabbed by the young people much easier. So Feynman, Professor Feynman says, if an apple is magnified the size of planet Earth, then the atoms in the apple are approximately the size of the original apple. Maybe he would have done some calculations or so, okay, in getting this analog. But these analogs are very, very helpful if you have to understand the size of the atom or the particle that we are talking about. Okay, so this sort of an analog can be taken up by the teachers so that we deliver physics in a slightly different way to the young people. Right. So when we say about atom and an apple magnified to the size of Earth or so, he also said that if you take a glass of water and then if you take these molecules, the water molecules, and then put them across 15 miles long, then you see them in a different way. You see each and every atom, you see each and every molecule. Okay? So it's like water magnified 1 billion times. That's what he's discussing in this chapter 1. The moment you magnify it to 1 billion times, we can see how they interact when they are in the liquid phase. Okay, that's what you see in this slide. The larger atom that you see is oxygen, the one in black, and then the white circles, which is the black with the black outline, they are the hydrogen atoms. So you see water molecules here, which are stuck together and nicely packed. But there is something important you have to notice here. They are random. It is amorphous. They are not oriented. It is not crystalline phase. It is randomly oriented. Okay. Right. So we are into the atoms. We can look at in the cartoon, of course. But the moment we heat it up, yes, there's no explanation needed for it. We are going to get these molecules there in the gas phase. You can see the steam, and then the molecules in the steam are much far away. So if you take the same dimension where you have the water molecule before, and the same volume or the same area, you have very few molecules. Fine. But if you take these molecules and you just compress them, because you know that density is proportional to the pressure. Okay. When you compress them, of course, if the pressure is going to be high, which means your number of molecules are going to be more. And these atoms are going to press the wall, and the wall is going to again, there's another force coming up from the wall. Fair enough. But why Professor Feynman is discussing all this in his chapter 1? There is something he is bringing up later in the chapter 1. Very, very important. Of course, for me, it was very, very important. Okay, I'm taking it from that angle because maybe in the other 2 slides, I will tell you why. So first, he talks about the liquid water. He talks about the steam. Then if you take the steam or just the molecules that are far apart, not just the steam, but they are just compressed, the molecules, of course, the density is proportional to the pressure. And you see these molecules getting together. And the other example he gradually builds up is that, yes, the same water molecule, now you freeze it. Now you are going to form an ordered, the molecules ordered in a certain pattern, and they form an ice. Okay, an ice crystal can be there. Water can be vaporized as this kind. Somebody's trying to hello. Okay, I'll continue. There's no sound. Right. So you can see the ice phase there. Okay, it is ordered. Then comes the other part of it. So if you say he's slowly building the case, okay, with the water molecule. Now the water is there, liquid water is there, and now you are boiling it. Okay, and it is evaporating. Evaporation is what is going from the liquid phase to gas phase. Okay, and it is evaporating in air. You can see the water molecules going off, and of course we have the oxygen and nitrogen in the gas phase, which is in the atmosphere. So it's like there is somebody talking in the background. Shall I continue? Or we wait for this voice? Okay, I'll continue now. The voice is gone. Okay. Right. Let me. Okay. Right. So we see the boiling is happening here. Okay. Fine. So we have taken all this in the physics way. Okay. We have these molecules or atoms which are in the amorphous phase. It's in the liquid form. Then you heat it. It goes to the steam. The molecules are far apart. And he says, okay, you can compress it and whatever the pressure and you are like bringing these molecules together. Before that, after that, of course, water when you freeze it, they get into an order form, and you can get this crystalline phase, no problem. And when you boil it, this is what is happening. Okay, you get evaporation. Then comes an important step. He brings it here. If you have some other like a foreign agent, sodium chloride and so on, introduced to the liquid water, then you see the water molecules try to drag the atoms of chlorine and sodium. Okay, that is a physical process which is dissolving. Okay, so you can see dissolving. Now I would like to ask a question to the audience here. You can email me if you find the answer. So you can see the water molecules surround an atom of NaCl or NaNCl, and of course it is dragging it off. Take a beaker of water, equal amounts of water, big, okay, and then the same temperature, every condition in 2 beakers of water. 2 beakers of water, every condition is the same. Okay, and 1 beaker you put a little amount of salt, and the same amount of sugar you put on the other beaker. So can you tell me which dissolves first? Is it the salt or the sugar? Okay, so take this question and we can discuss about this later. Right, so he says dissolving is happening and this is a physical process. Fine. Then comes the most important part where he is building this case one by one since the figure 1. Now we are in figure number 8. Here it's a chemical process. You're burning, carbon is burning in oxygen. Okay, so this is something very interesting. And carbon is burning in oxygen. Again, you see the same process happening. An oxygen atom comes, it is attaching to the carbon atom and takes the carbon away. Something similar you see here, and water molecule is coming, it's getting attached to the Na or the sodium atom or the chlorine atom, is taking that away. Here you saw that this is a physical one. Here it's called a chemical reaction. Chemical reaction is thing, but it's the atoms that are doing it, an atom or a molecule which is doing the same thing. This is where Professor Feynman builds the case, and it is very, very interesting to read this chapter 1 again. The other processes so far described are called physical processes. But there is no sharp distinction between the two, because what you see just before is a chemical reaction. And this is something extraordinary that is said by one of the finest minds in physics. Nature does not care what we call it. She just keeps on doing it. Whether you say it's physics or chemistry, nature doesn't have any distinction there. Okay, so the moment you talk about atoms or molecules and so on, the line you draw between physics and chemistry, maybe for our understanding, but nature has no discrimination in that. So in this case, okay, we don't go into the chemical reaction. This is where Professor Feynman was bringing up where this parts of science comes into a picture. Something much more interesting he gives us to think about. This is one of the most fantastic pieces of detective work that has ever been done, organic chemistry. And why he says that? Because suppose so far we have seen small molecules, right? Water or NaCl or so on. Suppose you take a larger molecule, for example, or some of these molecules that the molecules on your coffee, the molecules on your tea, these molecules are very, very large. Or the molecules that make our hair and so on. That's where he says, coming into the chemistry part. So how do you find the molecular arrangement here? Okay, and those days, how do you find? And that's in fact a wonderful thing. To discover the arrangement of the atoms in these enormously complicated arrays, the chemist looks at what happens when he or she mixes two different substances together, or many substances together. We do not know. The physicist could never quite believe that the chemist knew what he was talking about when he described the arrangement of the atoms. Okay, so it depends on the reader how they take it. Okay, the physicist could never quite believe that the chemist knew what he was talking about when he described the arrangement of atoms and in a molecule. For about 20 years, it has been possible in some cases to look at such molecules, not quite as complicated as this one, but some which contain parts of it. Because we are talking about a larger molecule. Okay, so we do it again. For about 20 years, it has been possible in some cases to look at such large molecules by a physical method. And it has been possible to locate every atom, not by looking at colors, but by measuring where they are. The chemists are almost always correct. So he's saying that, looking at the atoms through reactions had been happening for a long time. So again, these are supporting statements for saying this: the nature doesn't have any line between physics or chemistry. So we'll move further from here. Again, in chapter 1, there's something which I found. Feynman's time, in his time, it was a developing field, or the instruments are getting better and better. Okay, there's some line. This is something which I would like to point out. The atoms are small, like so small. Or the question he is posing, that how we know that the atoms are there. Of course, from the Brownian motion and so on, we know it. But can we see it? That was the task there in his time. So he says the atoms are so small that you cannot see them with the light microscope, the optical microscope. That's what he's referring to. In fact, not even with an electron microscope. Okay, but of course, after these things, he himself in his time would have seen that an transmission electron microscope can show you an atom. Okay, so we were able to see atom by atom. For example, you take graphene. Graphene, you can see atom by atom, right? You can see an atom of carbon. In fact, you can see the C60, which is of the size of about a nanometer or something. So you are able to see them atom by atom. All right. So the world has moved. Instruments are getting better and better. I'm not sure who will be covering chapter 3, but chapter 3 is where Professor Feynman has talked about the relations of physics to other sciences. So we'll be linking it to the chemistry, the astronomy, in fact, even geology. As we say, the atoms and molecules everywhere, and without them, nothing is there. Okay? So it's all related. On that day, we have been discussing on the inauguration day. I've been pointing out, that I may be pointing out that if you take the work of Professor Erwin Schrödinger, we know that famous work and so on. But how many of you know that he has written a book? What is life? It's like it is about the physics of a living cell, if I'm not wrong. That's what he talks about in that. Okay. So physics of a living cell, Professor Erwin Schrödinger has discussed. So we look at physics, yes. Of course, it's a part of the other sciences. And by reading the work of famous people, the finest minds in natural sciences, we gain, of course, more things. And Professor Feynman himself made a lot of statements, and there's one thing in particular was very, very famous. He said there's plenty of room at the bottom. Many of you might have come across this. He is mentioning about the nanoscience. There's a lot of things to be explored in the nano miniaturization and the nano world. That's what he says. There's plenty of room at the bottom. Okay. So with this one, we may, I don't know, like I said in the beginning, it is up to the reader now. Yeah, at what stage the reader is, it's up to him how he looks at the world through the chapter 1. Okay. So I'm pretty sure that even after 10 years, when I read the chapter 1 again, it will going to be a different way of looking at the world again. And the way how we take the sentences, what he has formed one by one, it will be definitely different to what we have come across. So here we have touched upon the chapter 1, but if you permit me, I would like to discuss a few more things which is in relation with chapter 1. I hope I can continue.
Yes, sir.
Yes, sir. Yes, sir.
Okay. So in the first slide, I showed you that this logo I showed you, right? Okay. So in relation to the atoms in motion, not just on planet Earth, of course, beyond planet Earth, and there's plenty of room at the bottom. There's plenty of room at the bottom, of course, but not on which world. We do not know. There's so many worlds around us. The advent of new technologies are telling us a lot more things which we don't even have imagined so far. So I'll come back to this logo again, but before that we'll move further. Right. As you see that nature does not have a line between chemistry or physics. It keeps doing things. So we know astrophysics, which is very well heard, and the word astrophysics is more common. Whereas astrochemistry is something which may be more common now, but not 20 years back. Right. So astrochemistry is something there. But if I ask you the question, what is the difference between astrochemistry and cosmochemistry? Will there be an answer? Can someone give a try? What could be the difference between astrochemistry and cosmochemistry? Anyone
Can I?
would like to try? Yeah.
Hello.
Go ahead.
Sir Bala? Yeah.
Yes.
So I guess. Hi everyone. I'm Manish. And I guess cosmochemistry is something related to the isotopic study of different astronomical objects and meteorites. And astrochemistry is related to the origin of dust in the space, out in the outer space.
Okay, so there is one answer here. We will look at it. Okay, so you say that cosmochemistry is the study of meteorites, right? Isotopes and meteorites and all that, and astrochemistry is the study of dust. Okay, so let us see, and whatever the answer is, I have the next question for you all. Who is an astronaut? Anyone? Because everybody knows, but I need the particular answer. Astronaut. Yeah, go ahead. Go ahead. Hello. Somebody was answering.
A person who travels in a spacecraft.
Yeah, a person who goes to space. Okay. It's called astronaut. Then who is the cosmonaut? Is there any difference between astronaut and cosmonaut? Anyone?
So there is a difference. Can you hear me?
Yes, yes. Please go ahead.
Yeah. Actually, the word, the cosmos, we use when we talk about the universe, right? And astro is related to the actually the theory which is related to the universe, but it is up to the some scale what we observe by some observation, like astronomy.
Okay, now
Uh,
we need
do
the difference. We need the difference between astronaut and cosmonaut.
Sir, I think.
Who is an astronaut and who is a cosmonaut?
May I?
In cosmonaut, the answer might be like the person who goes in space, but up to the larger scale. Larger scale means
Up to
the scale is higher. So, you know the scale of the
no,
universe is
no.
like
No.
a megaparsec.
No.
Sir, I think.
There's difference between astronaut and cosmonaut.
Sir, am I audible?
Yes.
Astronaut is probably American word and cosmonaut is Russian word.
Exactly. So astronaut is someone who goes to space from the American soil, and cosmonaut is someone who goes to space from the Russian soil. Okay, that's the difference. So now I go back to the same question. What is astrochemistry and what is cosmochemistry? Anybody? Anish, you want to give a try?
Actually, you can say I'm a person of cosmochemistry, but whatever I
Yeah, I
knew
know.
that I studied isotopic,
Yes,
you
I know
know.
that. Yes. So
So
what
that's
could be
why.
the difference? Yeah. See, astronaut is someone who goes to space from American side, American soil or so. Cosmonaut is somebody who goes to space from the Russian part. Okay.
Okay.
So now what is
So is
astrochemistry and cosmochemistry?
okay. So is it something related to astrochemistry? Is the American people studying about the structure and chemistry of
Yeah. So I'm
just
asking I'm asking the same question. Is that right? Is that true that astrochemistry is something from the American side and cosmochemistry is from the Russian side?
no. I don't think so.
It's not right, no? Yeah, correct. So there is something, atoms in motion or the molecules and something. So what is astrochemistry and cosmochemistry? Cosmochemistry, of course, you are right to some extent. It's the study of elements. Astrochemistry is the study of molecules. Okay, and these things bring all these atoms and molecules in motion. Okay, elements, of course, molecules. But when we look at the elements, so because from the chapter 1, it's like interesting that how we put an analog to people and how the interest is built, or looking at how things have been happening in the scientific world in the past. Now we know that there is a difference. Okay, how you name? Of course, we are naming things, right, based on a reason. One of our teachers used to say, let's do things based on reasons, not based on emotions. Okay, the reasons have to be put in the forefront. That's one thing important we have to take from Feynman's chapter 1. The reasons are very, very important. Now we know that elements and molecules, cosmochemistry, astrochemistry, fine. Something we can look slightly into detail when we talk about elements. How are they named? Naming the elements. Is there any link to the space science? Let's see that. So how they named uranium? Does anyone want to give a try? How uranium was named?
From Uranus?
Certainly, yes, because there was a new planet that was discovered, and then when the new element was discovered, they want to in honor of the new planet, they named it as uranium, as the planet Uranus. Fine. After discovering uranium, they discovered another new element. And how would they would have named it? after uranium? Any guess? You have seen it? No textbook, no
By
periodic
their
table.
moons, by the moon's
Neptunium?
name.
Sorry? By the moons of Uranus, you mean, right?
Or maybe
Someone says
Neptunium?
moon.
Sorry.
Exactly. After Uranus, they named it as Neptunium, honoring the next discovery of the planet Neptune. Okay, so it's Neptunium. Then after the finding the new element Neptunium, they discovered another new element. Again,
Plutonium.
how do you think they've named it? Exactly. After Neptune, we have Pluto. It's named as plutonium. Okay. So when you see this picture of Pluto, I would like to point out that those days, when we are students, and of course a lot of other our teachers will also agree with us, we know that as a planet Pluto is there, okay, but we don't have a picture of it. It's just one small tiny light. If you take a picture of a street light from far away distance, what you get is what is the picture we have? It's a tiny light, speck of light somewhere. But now the generation, they are reading about space science in school time and so on, they at least know how Pluto looks. So one has to spend billions of dollars, go for several years just to take a picture of Pluto. That is in fact is important in science. Okay, so you see uranium, Neptunium, plutonium, Uranus, Neptune, Pluto. The way how the planets are ordered, to go back to your periodic table. If you go back to the periodic table, you would see that the planets are aligned in the periodic table in the name of elements. Okay, so there is some reason which is there in science. Of course, in science everything has a reason. Like Mr. Feynman is pointing out, it's the truth that comes from experiments and so on. Okay, right. So you see, we have something interesting happening here, but from the the discussions that we had over the last 5 to 10 minutes, we know that astrochemistry is an unconventional chemistry. Okay, so when the atoms are in motion, which is not directly discussed in chapter 1 by Professor Feynman, but he has given the clues of it. It is hidden in his discussion. He talks about the water, and in a beaker, the water molecules, how they are arranged. He talks about when you heat it, you have the steam, the molecules floating around, and we very I can go to the slide very fast. I would like to show you that. So that right. So here, when the water is heated, they evaporate the molecules. It evaporates and then it converts to steam. So the molecules are very much far apart. Okay. Something similar is happening in space conditions. Or if you look at molecules beyond Earth or even beyond the solar system, the molecules are not close enough. They are not arranged in a close packing unless they were ice formed. Okay, but when they are in space, you can see there's one or two molecules or one or two atoms for every cc, which is very less. Okay, so we go back here to where we left. Right. So this is something very important for us, because molecules or atoms are not confined to what we have seen on planet Earth. If we go beyond the solar system, right? So there is a way that we have developed ourselves to understand these atoms and molecules, okay, using spectroscopy techniques and so on. Okay, I'll just go to the other slides. Yes, here. If you take out the comets, so far they have discovered plenty of molecules. Okay, I have stopped here in the year around 2010, because after that we have many spacecraft that have visited the comets. They have looked at even the tiny amounts of molecules that are present in comets. Plenty of molecules are present. Okay, that's fine. We know the conditions within our solar system in quite good numbers, because of a lot of studies using space-based telescopes and even spacecrafts have been done. But if you take the environment which is beyond the solar system, which we call the interstellar medium, where a new star is being born, okay, These are the places where they have discovered, in fact, more than 250 molecules to date. This is somewhat interesting. But if you talk to biologists, they say, no, we need molecules that makes life. But this is somewhat interesting to other chemists and so on. But if you talk to astronomers, they are quite excited. They say, we are getting signatures, spectroscopy signatures of atoms. Of course, they get signatures of atoms, which is the emission, okay, the emission lines. But in plenty, they get signatures of molecules. And targeting one by one at a time is very, very difficult because you need to have laboratory experiments, like Professor Feynman says. You need to have these experimentally proven. You need the truth. Okay, so you have to bring the conditions of space on planet Earth, study them here, and whatever you get using your spectroscopy technique, try to see what is present there. Okay, this may look like a fundamental science and so on. Of course, every fundamental science has some implications in terms of application for the societal benefit and so on. But today here we focus mostly on this part. I'm not going to go deep into the biology. When we talk about these molecules which are there and astronomers trying to decipher the signals that are coming, plenty of them. For chemists, of course, it is a little bit more interesting and so on, certainly. When lockdown was there in the year 2020, as we are discussing this, we can even look at it to see how science progresses even during difficult times. That is also important for all of us. Because a lot of things developed during the difficult times, like a century back. Science was thriving when the times were very, very difficult, and something we even recently experienced in our lifetime right now. In the year 2020, we had this lockdown. Of course, it's very unfortunate, but scientists never stopped their work. They kept doing things to the best they can. So we would like to thank the astronomers, because I'm an astrochemist, so we like to thank the astronomers. At the year of lockdown, they were unable to access the telescopes, whatever they've been using so far. Maybe the access time is limited because of restrictions and so on. So they had enough time to go through the data which they have taken in the past. Okay, and then they were analyzing it, they were writing up, and then they were submitting for publication. Eventually, the year later, the manuscripts were coming out. After that lockdown 2020, the year 2021 saw as a huge rise in the number of molecules that we know that are present in space. So anyone would like to guess how many molecules were reported in the year 2021, just after the lockdown? How many new molecules were reported, were discovered in the interstellar medium, the space where where a new star is being born? Or in general, you say the space which is outside our solar system. You just take it in general. Can you guess how many new molecules were discovered in the year 2021, were reported? Anybody would like to give a number?
50.
I'm not asking for the molecule name, just the number.
50.
How much?
50. 50.
50. Oh, right. You're very close, but not 50. I'll be happy if it is 50, but it's not 50.
Mm-hmm.
Nearly there. Okay, no problem. So if you add 20 and 21, it'll be 41. In the year 2021, it is 41 new molecules that have been reported. And this is today the highest number of new molecules that are reported since they started discovering molecules in the ISM. This is the highest number. You see, even tougher times, scientists are working. They are going through the best option they have, trying to see what they can do, okay, in whatever possible way. So this is one good example which is there in front of our eyes, right? So I think I'll stop here. Or if you want some 5 minutes of what we cover in the range, and the range of things we cover in our astrochemistry work in PRL. I just explained this slide and I will stop. Can I continue or? Hello?
Yes.
Okay, right. So this slide is my last slide. Right. So it's like not just that, of course, we've gone through many scientists, the work of many scientists before us. It will be a few decades or even centuries and so on, starting from James Clerk Maxwell and so on, Feynman. There are plenty of people you can name. But someone would like to, I'd like to bring it to your attention, is the mathematician Hardy, G.H. Hardy. He is a person who recognized Ramanujan and took him to Cambridge. So he, in his book, The Mathematician's Apology, he had written a poem, which I'd like to bring it to your attention. He wrote these 4 lines, which for me has a lot of deep meaning here, which is there for the humankind. He says, in the level sand between the sea and the land, what shall I build or write against the fall of night? I mean, in some way you can see this in a physics way. The time, okay, time and during the inauguration time, I think Professor Joshipura, someone mentioned that according to Professor Feynman said that whatever is happening or not, time is happening. Correct. So this is something linked to this poem. That's what I was taking it. The level sand between the sea and the land, what shall I build or write against the fall of night? So the time is running. There is a night coming every day and so on. So time is running. Okay, what we do? We ourselves are atoms and molecules. It's like what the documentary, and it's anonymous. I couldn't recall which documentary it is, but it says it is the universe looking at the universe. We atoms and molecules are looking at atoms and molecules and studying them. Okay, but as an astrochemist, if you want to slightly, change this poem in a slightly different way, or what if Hardy is an astrochemist? I would like to put it in this way. In the deep space, between the dust and ice, okay, wherever there is no energy, everything will be cold. Okay, that's where your background radiation is. Between the dust and ice, what bonds were made or destroyed? I mean, the chemical bonds that makes us, or makes the life itself, against the birth and death of a star. Because every star is a star and human being or life. A star has a life, and of course, we all have any organic life form has some timeline, right? In the deep space between the dust and ice, what bonds were made or destroyed against the birth and death of a star? Okay, so this is something. If you connect some of the thoughts that Feynman and Professor Hardy had against the fall of night, time is running all the time. Okay. Right. So this, just to give a summary of what we do in PRL. 10 years back, we used to call astrochemistry. We used to say astrochemistry and so on. And of course, meteorites and all these things. We can talk to Anish for more details on meteorites. They're experts. But later, while going through these molecules and understanding a few of these, in fact, in chapter 3, you can see Professor Feynman talks about physics and geology and so on. We thought it would be right to call it as astromaterial than saying astrochemistry or so, because astrochemistry, if you take, it is a bridge between astrophysics and astrobiology. Astrobiology people do because they would like to understand the origin of life and so on. So we say astromaterial. Why we say? Because you can talk about something which is ice in the sense these are atoms or molecules, or atoms and molecules which are frozen. There's no distinction which molecule or which atom it is. Anything, any atom or any molecule. Of course, you cannot freeze certain atoms or molecules. Okay, so you cannot freeze certain atoms. Of course, all the molecules can be frozen, to the best of my knowledge. Some atoms cannot be frozen. If the temperature is of the order of 5 Kelvin or so, even hydrogen will supply. Hydrogen atom is very difficult to have. Hydrogen molecule is okay. It's easy to have. Helium atom, the pressure has to be very high if you want to have an ice form or so. But molecules, you can have them. Any molecule that's frozen, you say as ice. On the other side, if the temperature is high, the dust particles. When you go out and you take the handful of sand, it's a dust. It's a space dust. Okay. But according to Carl Sagan, because we're talking about Feynman, but every scientist have something. They have discussed many things in relation to science. But according to Carl Sagan, and from the scientific truth, we know experimentally that the water we drink are delivered by the comets. So what we are drinking is cometary water. Okay. So on the other side, the temperature is very high because comets do have dust. It's a dust ice ball. Okay. This is a refractory dust. When temperature is high, you cannot melt them, you cannot sublime. They remain as it is, even at vacuum condition. That's the dust. So ice and dust and so on, we thought we should call them an astromaterial. Like Feynman says, there's no line. The nature has no line between physics or chemistry and so on, or biology. But we, from our experiments, we came to this thing that we should call them as astromaterial. And then, as other areas of research, of course, we employ spectroscopic techniques to understand about the physico-chemical nature. So we say physics or chemistry, there is something we use physico-chemical nature of it. Physics and chemics, like the more you try to understand the physics and chemistry nature, the chemical nature of it. As I said that day, there is a journal, PCCP, which is by the Royal Society of Chemistry, Physical Chemistry, Chemical Physics. So they say that you can approach chemistry through physics, and you can approach physics through chemistry. Okay. Right. So this area of research is more or less, I agree with Feynman, it's very difficult to say where the line is between physics or chemistry. In fact, the more you go deep into the research and you talk about larger molecules, we cannot say are we doing astrobiology or are we doing astrochemistry. It goes to that extent. When you look at the meteorites here, or the minerals, or large carbon structures and so on, eventually we end up looking at the origin of life. So everything, what you have seen the last 30 minutes, what you have discussed, everything eventually ends up to the molecules of life. The molecules of life, of course, are made in a big bath of chemicals. We do not know the exact pathway. We know some pathways, but we do not know the exact pathway which led to the final outcome of the first cell and so on. Okay. So when you talk about astromaterial, is of course it's high temperature or low temperature, and we talk about that it can be a residue, or you are getting a commercial sample and then trying to synthesize a residue on your own, whether you do synthesis or even look at the destruction pathway. You look at the large molecules, pH means polycyclic aromatic hydrocarbons. Of course, the moment you have pH, you can talk about graphene. Graphene can even come from elemental carbon. There is something called MAONs. It's a mixed aromatic aliphatic organic nanoparticles. This is something very important. That's where I would like to link Professor Feynman's famous statement. There's plenty of room at the bottom. MAONs, nanoscience. Without nanoscience, it's very hard to understand the MAONs. Okay, mixed aromatic aliphatic organic nanoparticles can be inorganic. Of course, inorganic chemistry will also be there, but again, when you say organic, inorganic, it's only for our understanding, how to, for the discussion purpose, but not like when something happens really in nature. So yes, we need almost many parts of science if you want to understand the astromaterial. Why we have to understand astromaterial? That's where you can get an answer of how life originated, or the molecules of life are made. Because you can ask Anish, meteorites do contain a lot of amino acids. Right. So here I will stop, and we are open for questions. Thank you.
Joshibra sir, are you there?
Oh yes, very much. I am here. Hello.
Yeah. At least you can share your views, sir, at the moment.
Oh yes. So if you give me some time,
Yes, sir. Sure,
I
sir.
can. Sure, sure. Very nice.
Sure.
Thank you, organizers, and thank you, Dr. Bala, first of all, for mentioning atoms of Feynman, atoms in action from Feynman to atoms in action there in astrophysics, astrochemistry. Wonderful. Thanks in particular, Dr. Bala, for mentioning the periodic table on which I will have to say something. I will say something.
Yeah.
I don't have the PPT, but running through the notes very quickly, based on first chapter and possibly something in the second chapter also. Oh, very interesting, quite interesting program. And in fact, it is like a conducted tour of Feynman lectures in physics. And our tour organizers are Professor Vinod Kumar and Dr. Sumesh. So we have to thank the organizers also, the Charusat University along with RC7. Yes, Richard Feynman, very unusual scientist, very unusual, very exceptional teacher that you can see on every page of this volume, 3 volumes in fact. At this stage, I am reminded of Ghalib, the Urdu Shair Ghalib. Yes, for Ghalib it is said, कहते हैं कि गालिब का अंदाज़े बयां और अंदाज़े बयां means style of presentation. So now we can say कहते हैं कि Feynman का अंदाज़े बयां और he has a unique style of presentation that you can see. Friends, I have not read Feynman lectures, say not in detail, but there are a few things which I like most. And indeed, what I like most is the way he has put the definition of time, as you mentioned, Dr. Bala. Not exactly a definition of time, but a clear way of putting the things which we know. Very unusual, very elegant, exceptional. What is he saying? He says time is what is happening even when nothing else is happening. How true, how simple, how elegant. So this is one of the things I like. And the interesting thing is that this kind of a definition, if you say, of time is not in the beginning. It's not in the first chapter. It is there in the 5th chapter. So that is also very interesting. It's truly great. We can try to imitate Feynman and say that space, like time, space is whatever is there, even when nothing else is there. And then we talk about matter which occupies space. And that is our traditional way of thinking. In our traditional way of thinking, we talk about time, space, matter, energy, and start with mechanics in our syllabus, as per the syllabus. But, you know, Feynman does not start with these things. He doesn't have a typical syllabus, traditional syllabus. In fact, he has his own way of putting the things. He has his own syllabus, let us say. And he starts with atoms in motion, as you rightly pointed out, Dr. Bala. Why atoms in motion? What is the purpose of talking about atoms in motion? He explains. Feynman explains this choice by a very elegant expression. I will look at the Xerox which I have on page number 13. This is the way in which the page numbers are given. Chapter 1, page number 3. Mm-hmm. See, what is this? What is it that Feynman is saying? If in some cataclysm, some chaos, some destruction, large-scale destruction, if in some cataclysm all the scientific knowledge were to be destroyed and only one sentence to be passed on to the next generation of creatures, what statement would contain the most information in the fewest words? What will be passed on if only one sentence with the fewest words has to be passed on to the future generation? And he answers, Feynman, I believe it is the atomic hypothesis or the atomic fact that all things are made up of atoms, tiny little particles that move around in perpetual motion, attracting each other when they are a little distance apart, and repelling upon being squeezed into one. This is elegant Feynman. So that is how he says that he should begin with atoms and atoms in motion. That was from the page 3 of chapter 1. Feynman talks about the micro world. He talks about atoms in the beginning. He describes processes like physical processes of evaporation, condensation, typically considering the water molecule, as Dr. Bala mentioned, and chemical processes also. So he tries to look at chemical process as something which can be understood in terms of atoms in motion, atoms in action. Feynman's lecture, Feynman's way of putting the things is always like a random walk. For example, when he mentions violet, and this is on page 4 of 14, page 14 of chapter 1. When he mentions violet, it is not the color. It is not one of those big 7 colors. It is a plant. He is talking about a plant, and he is talking about processes involving water and so on. So that is something very unusual about Feynman. He turns to basic physics in chapter 2, again in the question answer fashion, but always having atom in his mind, atoms in action. Focusing on atoms as particles, he says. He calls atoms the particles, and then of course changes to more fundamental particles. What kind of particles are there? What different kinds of particles are there? Feynman is asking. And the answer is well known, 92. Of course, actually 94, let us say, naturally occurring elements. Chemically speaking, they are naturally occurring elements 92 or 94. And then he's asking how they are connected. How are the atoms connected? Atoms are connected by interactive forces. And so he mentions electromagnetic forces. And then a step ahead, Feynman is now entering atom and talks about nuclei and particles. By that particle, he means elementary particles. And he's trying to describe the classification of elementary particles. In the process of this description, to explain the classification of elementary particles, Feynman recalls Mendeleev's periodic table, the periodic chart, as he says, and periodic table of atoms or elements is the usual arrangement of atoms or elements in terms of their chemical properties, but he is trying to draw the analogy with the elementary particles. Later on, Feynman discusses more details of the periodic table, not just Mendeleev's periodic table, but the periodic table that we have today. In volume 3, he has a quantum mechanical view of a hydrogen atom and periodic table. And so that is more technical, more details. In between elementary ideas of atoms and the quantum mechanical view of periodic table, we can have some qualitative ideas. And I wish to share with you, friends, that the finest creation of human brain, one of the finest creations of human brain is periodic table of elements. It has been developed after attempts and atoms. And well, you may say it is all chemistry. Why should we talk about periodic table here in physics? Well, my friends, it is not just chemistry. It is based on physics, and it involves a lot of physics. As we know, the modern periodic table is based on the atomic number Z, number of protons in the nucleus, and therefore the number of electrons in the neutral atom. And therefore, we talk about mass number A. This is well known. Mass number A equal to Z plus N, where Z is the atomic number, N is the number of neutrons. So when the neutron was discovered, the whole system, whole classification of the periodic table became very clear. And so this is how physics is involved in the periodic table. We need not go to quantum mechanics to describe the qualitative aspects of the periodic table. In fact, we can try to understand the simple ideas and try to see how order was created out of disorder. When nothing was known, gradually people started classifying, analyzing, and today we have the periodic table of elements. It starts with hydrogen, Z equal to 1. On the left hand side, the topmost is hydrogen. Far off there, on the right hand side, is helium. Sometimes in my class, I used to call these as not only atomic numbers but roll numbers or seat numbers. So at roll number 1, we have hydrogen atom, Z equal to 1. On the left hand side, you have hydrogen. Z number 2, the roll number 2 is sitting there, helium. 3 is again below hydrogen, lithium, and so on. You can try to have some sort of analogy. But the point is that physics is involved, and there are 18 columns, 18 columns and 7 rows. 18 columns are known as the groups, and there are periods and so on, up to 92 or 94, let us say. What is this confusion? I will ask, and I will leave it for you to find out. What is the number of naturally occurring elements? Does it stop at Z equal to 92, or should we also mention Neptunium and plutonium as available in nature? It can be synthesized, fine, but should we also say that naturally occurring elements are 92 or 94? I leave it to you. But certainly, there are several man-made or synthesized elements. One of the reasons for mentioning periodic table is that it explains the important concept of isotopes. Iso means the same. Topos, or top corresponds to position. Position where? In the periodic table. So in the periodic table, there are atoms which have the same position, but they differ in their structure, number of neutrons in the nucleus, and we talk about isotopes. There are a few other things. For example, carbon, as he mentioned. There are wonderful elements. Each and every element in the periodic table has its own speciality, its own wonder. But carbon is indeed a wonder element. Carbon, the wonder element. This was mentioned by Dr. Bala. But carbon occurs in allotropes, and today we talk about not only diamond and graphite, but also talk about fullerenes, the nanotubes, and graphene, thin layer, one atom layer. And if that is not enough, in the periodic table, you go below carbon and you will come across silicon and germanium, and they are useful for semiconductors. It's very interesting to see how the physical properties change from carbon to silicon to germanium and below. All I want to say is, try to explore the periodic table in terms of physical concepts, and you will enjoy it more. I think this is what I had in mind. Thank you for giving this opportunity. Thank you, Professor Vinod Kumar, Dr. Sumesh, and I thank all the participants. Very nice. Thank you.
Thank you, sir. Thank you very much for your enthusiastic, energetic, in fact, presentation. I hope participants also cherish the same thing. Yeah, thank you, sir. As you said, sir, Dr. Bala kept the same thing over here. There is plenty of room at the bottom where he has stopped 80 years, 80 years ago, the topic he thrown. Now, if you start a series, I think there may be another 2-3 books can be covered. That much we have really developed now. So this particular chapter itself, if you consider, I think there are a lot of things needs to be still worked out for anyone because there the bulk particles and all that, now it is nanoparticles, like what you said, graphene is going to rule the entire electronics in future, the foldable flexible type of devices and all that. So what he conceptualized several years ago, now it is a reality which is happening in front of us. So there are a lot of things since just one chapter, if you consider itself, one can come out as an outcome, because the output ultimately is something converting into the form of book and all that. So there are lot many things, I guess, we can work out jointly in this, considering each and every chapter. And every concept what he proposed to those time and is really apt at moment also, how fantastically it is working. Even some portion of that still we have not covered in terms of electron microscopes and the scanning electron microscopes, transmission electron microscopes. Now it is a reality where nanoparticles, their applications, where that is because of that only. So everything is covering again because of the same concept of atoms and motion of atoms, wonderfully, which is happening. So I think.
Professor Ahluwalia is raising hand, I think. Professor
Hello,
Ahluwalia,
sir. Hello, sir.
IAPD President.
Ahluwalia, sir. Hello.
Mike,
Can you
your mic.
unmute, sir? Hello.
You have to unmute him.
No, he can unmute himself.
Please unmute.
Manan, can you unmute him?
No, sir, he can do this. Otherwise, we cannot do unmute.
Ahluwalia, sir. Hello. Can you unmute yourself?
I am unmuted now. Am I audible?
Yeah.
Okay,
Fully,
all right.
wonderful. Yes.
Okay, all right. So actually, when you come to new platforms, you have to learn the new tricks.
Yeah, sure.
So thank you very much. I was delighted to be part of this lecture, and I just wanted to say one or two things.
Yes.
One is this, that you will notice that in Feynman lectures, Feynman devotes three first chapters, chapter 1, 2, and 3, for creating the curiosity of the learner itself. He could have started from the fourth chapter itself, because he would have said, okay, physics deals with matter and energy, so let's begin from here. But he doesn't begin from there. He actually takes 3 chapters to lay the table for a very good what you call party of physics. That is what is very interesting part of that. That's something which we must really remember. And he always used to emphasize, whenever he used to talk to people, lay persons, and he was very fond of talking to lay persons also, that one of the first things which we need to study science is, or the things around us, or the nature around us, is to be curious. This is one very, interesting characteristic which gets revealed in the first 3 chapters itself. Second thing which I want to mention is, and that is a kind of a small comment, in a way supplementing what Professor Joshipuraji was saying, and that is this, that Mendeleev actually gave us the periodic table. And if we look at those times when he gave that periodic table, what he did was, he was trying to teach his students chemistry. And he wanted to teach it in such a fashion so that he doesn't have to teach, say, when he is talking about halogens, all the halogens. If he teaches chlorine, the properties of the rest of the halogens should be clear to the students. So that was his dilemma actually, when he started thinking about some kind of a pattern which exists in chemistry. And Professor Bala actually was pointing out to that very interestingly. That was very interesting part of his lecture. And the beauty of recognition of that pattern was this, that he found that in that pattern, somewhere something is missing. And he wanted that maybe in future we will come to know that what is that piece which fits in here. And it is, very satisfying also for a person who makes such a prediction. And in his lifetime itself, people find that, yeah, here is an element which perfectly fits in at this particular place. And that happened with Mendeleev and Mendeleev's periodic table itself. Another very interesting question which Professor Joshi raised was this, that periodic table is chemistry or physics. And there is a very interesting part of it. Before the beginning of 20th century, it was all in the hands of chemists. But when we moved to the 20th century, right from the very beginning, when Madame Curie came on the scene, we find that the discovery of new elements was taken over by physicists, because the discovery which used to be done with the help of chemical methods, now people said you can do it with the help of physical methods also. And one of the very big dream which in this pursuit was fulfilled by, say, man was this, that they were able to convert one element into another, a dream of an alchemist. Alchemists always wanted, how can I convert base metals into gold? And transmutation is nothing but that kind of a situation which happened. And by, I think, late 20s, Dirac made a statement that whatever chemists wanted to actually know about periodic table, now we know how it all happens. And everything which we wanted to discover out about chemistry has been, discovered now. It's only a matter of, analyzing things further. But we know that why a particular reaction takes place, what is the meaning of mechanism of a reaction, that became very, very clear when we understood the electronic structure of elements itself. So these are, fascinating things which emerge. And then Feynman comes and he puts, I think, whole of the, what you call crux into saying this fact itself, which Professor Joshipura underlined, that if you want to tell future generations, if everything gets lost, you only need to tell them that it is a matter of atoms being arranged here and there only. What I will do, Professor Sumesh, I have a link for a very interesting video. And the title of that video is Mystery of Matter, Unruly Elements. It is actually, I will send you in my WhatsApp also, or maybe I will try to post in the Microsoft Teams also. I think it is worth watching. It is about 1 hour long, but it's a very, very inspiring story when chemistry and physics are being taught together in the discovery of these elements. And the title Unruly, because before Mendeleev, people were finding it very difficult to how to really look at all these elements which were getting discovered. And I think our group who has come to appreciate what Feynman has left as his legacy in the form of these lectures, they will enjoy it very much. Thank you very much, sir.
Thank you, sir, again joining here. Now, I guess participants, if you want to share with our mentors, Dr. Bala is there, Joshipura sir is there, Alwalia sir is there. Some of you want to share your views. You can unmute and speak, it seems.
Good evening, everyone. Am I audible? Am I audible?
Yeah, audible, please.
Yes, thank you so much, sir, and Charu said for giving us this opportunity. And it was a wonderful lecture by Bala, sir. I just would like to comment on the that origin of life thing that caught my interest because at present we are working on the such kind of molecules, that is scattering study we are doing it on such kind of molecules. And while referring to the numerous papers, so it caught our attentions in a way. It's really so interesting to study such kind of papers, new papers, what Professor Bala was talking about, that plenty of new elements were discovered in 2021. So I would request Bala sir, if we can have the list of those molecules which are identified in the interstellar spaces in recent years.
Yes, certainly. I will send a link to Professor Sumesh,
Yes,
so
yes,
that he
thank you.
can share with our participants.
Thank you, sir.
Yeah, thank you.
Hello, sir. Am I audible?
Yes, yes.
Yeah. May I discuss something, sir, regarding the today's chapter itself?
Please, please.
Yeah. So, sir, so first of all, thank you very much, Charu said, and the team for inspiring us and for creating this platform. Thank you, Bala sir, for the nice lecture, and also thank Professor Joshipura sir. Sir, I wanted to know, or I wanted to discuss that if we can, uh, after finishing this chapter only, if we can combine the concepts of like what we have discussed today, astrochemistry, biology, astronomy, and considering the atomic hypothesis, if we can design some, simple some problems that might help us as well as our students to get more deeper insights into combining all these things together and make a link between them.
I would like to say something here.
Yes,
Right.
sir.
So when we are discussing about Mendeleev and the elements, it was so difficult in Mendeleev's time before the way how it is ordered. So we are right now in a similar situation in astrochemistry, you can say, because in astrochemistry it is very difficult to say which is a simple molecule and which is a complex molecule. On planet Earth,
Yeah.
you can say, if we say a simple molecule and a molecule with few atoms, it is a simple molecule, it is a simple one, and a molecule that is larger is a complex molecule. But if you look at the chemistry that's happening away from our solar system, to date, we have the difficulty to say which is a simple molecule and which is a complex molecule. Because in the literature, you can say, okay, water, ammonia, methane, all these things are simple molecules and so on. Because they are, water is 3 atoms, ammonia is 4 atoms, methane is 5 atoms, and so on, fine. But there is a difficulty. There are molecules which are known to be present in the ISM. For example, it is a molecule which contains 4 atoms, okay? And all 4 are different atoms. HOCl, isocyanic acid. You have all the 4 different atoms making one molecule. So these are the molecules that is bringing the question, how do you classify which is a simple molecule, which is a complex molecule, if you look at chemistry beyond the solar system. Okay, so this is, again, is like scientists have faced in the past. It is up to us now how we provide an answer to the future generation of scientists. Okay, so just don't like to point out that. So if you look at it in a way that, of course, complex problems do exist. At the same time, we have simple problems in front of us, we need to find them. The same way, if you look at the spectroscopy part, to date, we do not know if you look at the vacuum ultraviolet wavelength of molecular ices, even for a simple molecule like hydrogen peroxide, we do not know how the spectrum will be. Okay? And in fact, if you see 15 years back, nobody had an idea of how the spectrum of ozone will be in the vacuum ultraviolet when ozone is in the present of in the form of ice. So it was only 15, I think, no, not even 15. So only 10 years before this problem was solved. So likewise, if you look at each and every particular area, there may be simple problems that are still hiding. We have to bring it out. Of course, it's the teamwork that will bring out, and discussions like this will be useful in that way. Thank you.
Hello. Yeah, sir, my point was so that means we have several known molecules, and we know the environment where they are formed. Like for example, on the simple ices, they are formed in certain environments in space, right? So knowing these facts, if we can, we have to have some inputs, of course, because I'm not an astrochemistry person. But if you can, if we know some guidance from you, and if we can get some guidance from you, and like for example, just to how to explain? Yeah, just to design for the sake of just to understand, if we can design some simple problems that in such environments where means how is the pressure, how is the temperature condition, and what type of molecules can grow. So if we can start designing, or this type of problems to understand these processes more deeper. This just I wanted to.
Yeah, sure. We can we'll discuss about this. Sure. Yes, there are plenty of problems. Like Feynman says, plenty of room at the bottom. If you take every object in the solar system, there's plenty of problems.
Yeah. Thank you, sir.
So we'll put it in Feynman's words. Yeah. So that was Hardik, right? Hardik Desai. Who was asking the question?
Yeah, he was Manish.
Know the name. Manish.
Your,
Okay.
I asked you about the list of molecules.
Okay. Sorry.
Yeah.
So we will discuss further about the problems.
Yeah.
Sure.
Thank you.
So when you say that, one thing I would like to point out, in the year 1996, Hubble Space Telescope was observing one of the moons of Jupiter, and they got a spectrum in the ultraviolet. That spectrum had two peaks in the ultraviolet. One was solved the same year, 1996. They told, okay, this peak is because of ozone, and the second peak is still, even to date, it is unsolved. It's more than 25 years. In the ultraviolet, there is a band which is so. The moment you look at different places and so on, maybe it is a simple spectroscopy thing for us on planet Earth, but for another body where the conditions are very different, they still exist, unknown. So there are many unknowns. We will discuss.
Yeah.
Thank you.
Yeah. Thanks.
Bala, one more thing that I would like to draw attention. Recently, I think James Webb Telescope had recognized the many molecules in the interstellar spaces, if I'm not wrong.
Okay. The JWST is going to revolutionize this area. There's no doubt about it. Yeah, it is. We are looking at it. It is coming on. Recent work last week, they talked about methyl ion, CS3+. CS3+ was known in theory so far, but now there is a discovery. It was in Nature. It was an accelerator article. So yes, so whatever was known in the theory, in theoretical chemistry, they have been finding proofs. Like what are the Feynman's words? The experimental truth is coming. They got the signatures of CS3+.
CS3+ or
CS3+. Only, that's all. Only CS3+.
CS3+.
Yes.
Oh.
It is a JWEST finding.
Okay.
It is only 7 days old, I think. 7 days, 6, yeah, around 7 days old.
Okay. Thank you.
Yeah.
Good afternoon, sir. Am I audible?
You are audible, and along with that, you can just tell your name so that vendors also can familiarize you, recognize you.
Hello, sir. Dhruvid Pancholi here from Baroda. Hello.
Yeah, we can hear you.
Yeah. Sir, while reading this chapter, first I had some doubts that here is written that helium is not freezing at its absolute zero temperature. Why
Helium
is it
atom.
So? Helium
atom. Yeah.
It is not
Even
freezing at a even at a absolute zero temperature.
It has to bind to the surface, no? It has to bind to the other atoms and so on. So you need sufficient energy. But you can freeze, you can make helium ice when the pressure is very high. Whatever they have told must be for the normal pressure. Okay, but if the pressure is, if I'm not wrong, 240 psi or more, helium will condense if the temperature is around 10, less than 10 Kelvin or so, something like that. But it should be very high pressure.
Okay.
The same
And
way
sir,
you cannot have hydrogen
question.
atom. Yes, sorry. I just extend the answer a little bit. Same way you can have hydrogen molecule in the ice form, even if it is ultra high vacuum, 10 to minus 9 millibar or so on. If the surface temperature is 3 Kelvin or so, hydrogen ice can be there, but not hydrogen atom. Okay, so the pressure has to be, I mean, the pressure plays an important role when you want to change the phase of an atom or a molecule from one to the other.
Okay. And sir, one another question is that why there is a hexagonal shape while being snow?
Oh, that's how the arrangement. See, it is to do with the atoms choose to do it, no? Because that's the least. There are not just hexagonal shape. There is a cubic also for ice, not only hexagonal. I don't know whether, because there are, if I'm not wrong, there's plenty of phases there. Must be more than 8. Depends on the pressure and temperature. That will decide whether it's cubic or hexagonal. So it's a crystal growth they do.
And sir, that is why the anomalous expansion is there in a water, because space is there, and then again when.
Okay, so I'll put it through in the way how we see it in the ultra high vacuum. Okay, so if you say water ice is present from 10 Kelvin, 50 Kelvin, 100 Kelvin, or 150 Kelvin, and so on. Okay, there what happens? The pressure is of the order of 10 to minus 10 or 10 to minus 9 10 millibar and 10 to minus 9 millibar. We have this water ice which will be subliming at a temperature around 160 Kelvin or so. Okay, 160 Kelvin. Subliming in the sense it goes from ice phase to gas phase. Okay. On the other side, if the pressure is low, 10 to minus 7, 10 to minus 6 or so, same water ice will sublime at 180 Kelvin or so. Okay, the temperature of the sublimation temperature is increasing. And if your water ice is under in a chamber which has a pressure of 10 to minus 4 or minus 3, then the sublimation temperature is even higher. It should be 220 or 230 Kelvin. Okay, so it's the vapor pressure that matters. So if you have an ice, there's a vapor. Okay, so how good the vapor is, or it's like I cannot draw it here. Okay. So how good your vacuum is, and the vapor is being pumped off, the vacuum is sucking the molecules out, right? So they go off quite faster. So there is a layer of it is a vapor pressure that's slightly building up when you achieve the temperature, because the molecules are moving. Okay, they tend to move. They have to. That's why your 10 Kelvin, if you have the water ice, it is amorphous. But the moment it crosses 140 Kelvin or 145 or 150 Kelvin, around that temperature, it arranges itself into the crystalline form. It can be sometimes it's cubic, depending on the condition, it can be hexagonal. Okay, it is the movement of molecules that matters, and the condition that leads to these effects.
Okay. Thank you, sir. Thank you, sir.
Yeah, and also the porosity will also have an effect, because at 10 Kelvin, water ice is more porous. The moment you heat it, molecules move and they tend to occupy the pores so that they condense. The density is more at high temperature than the low temperature, and this is all measured.
If I say something. Hello.
Yes, sir.
The question is about the anomalous expansion of water. And the idea is that ice is a rather open structure. So there are 4 molecules surrounding one particular water molecule in ice structure. Now, when it melts, this will start collapsing, and you will have a more closer packing, and then freely the molecules are moving when they come to liquid phase. And so there is a situation where you have the anomalous expansion. Regular behavior will come after 4 degrees Celsius. That's the idea. Ice is an open structure. That's why ice floats
and that
water.
Yeah.
And the similar thing is there at 10 Kelvin also. That's what I'm pointing out. Whether it's 0 degree or doesn't matter. So even at 10 Kelvin, you have this.
Oh, thank you.
Yes. So, and the pressure is very, very low, no? So 10 to minus 10 or minus 9 or even minus 7 doesn't matter. When water is pure, same at 10 Kelvin, you will experience this. It is very less dense. So can I say one more thing? Yeah. Okay. When you talk about this, if you take Titan, one of the moon of our solar system, one of the moons of Saturn, there you see ice, which is hydrocarbon ice, floating on hydrocarbon lake. Okay. So it is not just with water; it's the other molecules also. You will experience this, but the conditions are slightly different. Okay.
Okay, if there is no question, so we'll shut down this, or we can stop this meeting. Hello, sir. Sumesh, sir.
Any teachers, participants?
I think Vijay sir wanted to tell something.
He can unmute and speak. Anyway, I don't think he is able to do something.
Some mic issue, I think, sir, written in a chat box.
Okay. So I think Dr. Bala, Joshipre sir, Raghavalya sir, well begun is half done. So we have started a very good session over here today with an enthusiastic participation. Yeah, sure. Thank you. So with all your inputs and the supports, we will continue this session as per our schedule. So the details will be again shared in the Teams box continuously, and all of you can share the messages in that, and it will go to individual continuously, and some attachment and everything. The Microsoft Team is a very user-friendly kind of thing, so we can do all the communications in this. and every participants, even the mentors, everybody can see, all can give your inputs continuously. So let us be this as a continuous platform, and we'll interact frequently. So with these inputs, I once again thank you all. Thank you to all our esteemed mentors for sparing their time. I hope in the future session also they will join us along with others. So with this, I wish we wind up over here this session. Thank you all. Thank you very much. Thank you.
Thank you, Dr. Sumesh. Thank you, Dr. Sumesh, and thank you, Professor Vinod Kumar, Professor Joshipura, and all the other participants, Professor Aluwalia.
Yeah.
Thank you all.
Thank you. Thank you very much.
Thank you all.